Hello class, this week we're covering measures of dispersion, which is also sometimes called measures of variability. Now, this is basically going to be a continuation of our discussion of descriptive statistics. We talked about measures of central tendency last week. This week, what measures of dispersions are, where measures of central tendency basically tell you a particular centerpiece of your data. The measure of dispersion kind of tells you how spread out your data is, or just how different the data is from each other, your different data points. You can basically summarize measures of variabilities as essentially variables, or let me restate that, a summary measure that essentially tells you how different your variables are from each other or from a central score, because some of the measures of dispersion or variability that we'll be looking at essentially tell you how different your various variables are from the mean. Okay, let's move ahead and talk about some of the easy ones first. But our objectives here, we're going to basically be able to describe what variability is and various measures of variability. We're going to look at the range, variance, standard deviation, as well as a few others in there, but those are our three main ones. We're going to learn how to compute each of these, and that's what we're going to do. So first, though, I want to talk about variability. It's this discussion on, okay, just how different your different values are within your variable. Essentially, variability, you want to remember this definition, it basically just means the degree to which individual data points are distributed or spread out around the mean. Easier way to think about it, variability, just how much your different data points vary from each other and the mean. To give you kind of an illustration of this here, we have two graphs here kind of depicting two different levels of variability. This one here, if our mean was right here at 50, you would essentially see, or somewhere around that area, you'd see there's very little spread here. Where this one has a lot more spread, so we would say it has a greater amount of variability. Again, all that really is how spread out your data is around that mean, and the more spread out it is, the more variability you would say you have. Just for another example, let's look at this from a numeric example. Take a look at the following two variables and their sets of values. Let's say we have this one here, the mean of 75, and this one here. They both have a mean of 75. So if we were just comparing on the mean, we wouldn't have a lot of information here, and it wouldn't really seem that different. But looking at this, which of these two do you think has higher levels of variability? Well, it's pretty obvious here that our second one here has a higher level of variability. You can see it ranges all the way from 30 to 90, where this one only ranges from about 70 to 80. Now that's one thing that you can get. It's interesting to see that you can actually get the same mean but have a pretty drastic difference in variability within your score. That's why it's important to look at these various measures of dispersion or measures of variability to get really a true picture of what our variables look like. But okay, moving on, let's actually get into some of our measures of dispersion. Now the first thing, most of the ones we're going to cover in this class are for, or within this unit, are for interval or ratio level data. But there is one measure of dispersion or measure of variability that can be used for nominal or ordinal level variables. Remember, nominal and ordinal is basically when your numbers are kind of arbitrary and it's just kind of telling different categories within your variable. There's still one measure for that. It's called the variation ratio. Now, if you remember anything about from last week, about when we were talking about measures of central tendency, if we're looking at nominal or ordinal data, the only measure of central tendency, if you remember, that was fit to be used was the mode. And again, the mode is just a variable that tells you which value is most occurring in your data set. Well, the variance ratio actually kind of looks at the mode that determine the dispersion within your nominal or your ordinal variable. Here's our basic formula for this. Now we'll break it down in part. This V here basically stands for variation ratio. You'll sometimes see that put as VR. Let's forget about the 1 minus here and just look at this part for a second. This FM here stands for frequency of the variable that's in your mode, basically how many are in that mode, and then you divide that by n, the total number or values within your variable. And what's that going to give us? Well, that basically gives you, again, that proportion of how many values are represented in the mode. The proportion of your mode, basically. Now this is where the 1 minus comes in this formula. Why we subtract this from 1 is that it basically gives us the flip side of that and tells us, okay, the proportion of values that aren't in the mode. And that's all the variation ratio really tells you, is the proportion of variables that aren't represented in your mode. So it's a pretty simple, pretty straightforward measure of dispersion, again, only useful for nominal or ordinal data. Let's give an example. Let's just go back to our example from a previous quiz where we asked, okay, looking at various robberies, what kind of weapon was used. And let's say we had a gun was used in 7 robberies, a knife in 4, and a banana in 1 robbery. That guy was a very bold robber in that case. So if we plug these values into our formula we have up here, where we get v equals 1 minus 7, because guns are mode and it's got a frequency of 7, and divide that by our total number, which is 12. So we'll do this a time. So we do this part first. Again, remembering our order of operation. That gives us 0.583 if we actually went and did 7 divided by 12. So now we got to take 1 minus 0.583. This 0.583, again, that basically represents the proportion of variables in your mode. And we can convert this to a percentage really easy just by timesing it by 100, which would give us 58.3%, which basically just means that 58.3% of the variables are in the mode. Again, we subtract 1 minus this, gives us the flip side of that, which is 0.417, or 41.7% of the variables, or of the values are not of that variable, are not represented in the mode. So again, that essentially gives you the flip side there. So you'll remember how to basically do that one. It's fairly easy, but we're going to move on now to the ones that we're going to be using a lot more in this class, and they're going to be useful in a lot of other things later on. And these are the various measures of dispersion that we use for interval or ratio data. And the first one we can talk about really easy is the range. The range. This is essentially just the distance from your lowest to your highest score in your variable. So your lowest value to your highest value, and really easy to compute that. You just take your highest score, subtract your lowest score. So subtract your lowest score from your highest score, or your highest data point, and that gives you the variable. So let's say that we had highest score was 75. We're still looking at age of people in the class. Lowest age was 2. We would have a range of 73, because all we do here is subtract the highest, 75. It's our oldest person in the class, by our youngest person, or in this case, since that's what we're studying, highest by lowest equals 73, so we have a range of 73. So that is by far the easiest measure of dispersion that we have. However, the range really doesn't give us that much information. I mean, again, it tells us, okay, what's the distance from our highest and lowest value, but that really doesn't tell us very much. And the reason the range is essentially not a super useful measure dispersion is because it only takes 2 data points, 2 values from your entire grouping of values. So you might be missing a lot of information in between. Now our next 2 that we're going to explore are a bit more complicated, but they take this into account and give you basically a fairly decent representation of the spread of all your variable, or all your values in the variable. And these are the variance and standard deviation. Now these are the 2 that you really want to pay the most attention to. Again, range is super easy to calculate. Variance and standard deviation will be a little bit more, so you want to really make sure that you understand this, and we're going to be using these a lot in this class. A lot of the stuff that we do later in this class is going to build off this knowledge. Basically, both the variance and the standard deviation tell you how much the values in your variable differ from the mean, or how much they're spread out from the mean is a good way to think about that. Now, essentially, the standard deviation is just an extension of the variance, which we'll see later. But the variance, if you had to put it as far as a definition, it's the average square difference of each score from the mean. Now that might sound confusing now, but once we get to an example, that should make more sense to you guys. Now just to kind of give us we'll go over variance here first, because again, the standard deviation is just a simple addition to how we get the variance, really. But the variance is, again, another way we can say this is the sum of square deviations about the mean divided by the sample size minus 1. That's one way we could talk about the formula. There's essentially two different formulas we can use to calculate this. The first is what's sometimes called a definitional formula, because it really shows you the underpinnings of how this works and what it does. And the other is the computational formula. And we're going to do an example with both of these. I'm going to do the definitional formula first because it really shows you the inner workings of variance and what it's really telling you. So we'll come back to this. The one thing I want to talk about real quick though is population versus sample. If you're trying to get the variance and standard deviation of a population, the formula is basically the same, but it's going to have different notation. So the population variance, you actually have this represents that, and then obviously you're going to have uppercase N representing the entire population. And here, instead of having the mean of the sample, you have mu, which again, if you remember from our earlier chapters, represents the mean of the population. Otherwise, you calculate it the exact same way, so we don't need to worry about sample versus population here. So we're going to talk about this in terms of samples, though, because that's how we're going to usually be using it. So let's see, how do we calculate the variance? Well, first, let's say that we have a listing of scores. We have this variable here. Let's say that this variable, let's say this is the amount of time that it takes a burglar to case a property before breaking into it. So we have a couple of different scores here representing different burglars and how long they'd say it takes them to do this on different trials. And so first thing we're going to do if we're calculating the variance, and this first example here, we're going to use that definitional way of doing it. So the first thing, again, we have our listing of variables. Under that definitional one, the first thing you want to do is add these all up and get the mean. So again, add them all up, divide by the amount that there is, and that gives us our mean. Okay, if we went and we did 13 plus 14 plus 15 plus 12 plus 13 plus 14 plus 13 plus 16 plus 15 plus 9, and divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would give us this mean, which I've already calculated here, which is 13.4. So the first thing we do when calculating this, we list out the scores and compute the mean. Pretty straightforward, pretty easy there. Okay, what's the next thing that we do? Well, the second thing we do is subtract the mean from each score. So 13 minus 13.4 gives us negative 0.4. 14 minus that, 0.6. 15 minus 13.4, 1.6. So we take that, and if we did that for every single variable, we essentially get x minus x bar here. Now, one thing I want to stop and talk about here is that sometimes people try to just go this far and think that that's far enough as far as calculating the spread of from the variables from the mean. But the problem with only going this far is that if you added these all together, you always get 0, because the negatives and the positives are always going to cancel out, because your mean is the exact, basically the center of that distribution. So this is the reason why we actually go on to the next step, which is kind of the main part of the variance here, and that's that we take this x minus x bar that you calculate again this way. You want to chart it out again and subtract the mean from each variable, and you get those scores. Next thing we're going to do, you want to square each of these values that you just calculated, which the big thing that does is it makes all the values positive. So when you add them all together, it no longer equals 0. So we do negative 0.4 times negative 0.4 would give us 0.16. Negative 0.6 times 0.6, 0.36, and so on and so forth. If we went all the way down, we would get all these values. Now our next step, so what have we done so far? List and compute the mean here. Subtract the mean from each score, square that, Now, step 4, sum these squared variables. So you got your squared values here. Now you add those all together. So sum of x squared equals, I already calculated this here, so if we add this all together, we get 34.4. Alright, so there's only one more thing we got to do here. And I brought the formula up here so we could kind of walk through this again by looking at the formula. What we basically just did by going through all these steps is get this top part of our formula finished. So again, we got the mean, which we needed for this, x minus x bar. This is our x minus x bar. Okay, then we squared that and summed it. That's what we did to basically do this. And that gave us 34.4. So now we divide that by n minus 1. Count these up. We have 10 values, so minus 1, 9. Gives us 34.4 divided by 9 equals 3.82. So our variance here is 3.82. So pretty simple to calculate. Although you have to pretty much follow those steps if you calculate it using the definitional formula. This is how you have to do it. And if you get a lot of variables, or I keep switching my words around. If you get a lot of values in your variable, it could get kind of cumbersome after a while. But that's why I'll go over to the second way to calculate this here in a bit. But the other thing I wanted to just talk about real quick is why we do the n minus 1 instead of just dividing by n. All you need to remember for now is why we do that as part of our formula for this, is that it essentially gives you a less biased estimate, because our variance of our sample can kind of be seen as a lot of times when we're doing research, we try to actually take that and then compare it to our generalize it to the population. This makes it less biased if we do that, because the n minus 1 gives us essentially a more conservative estimate. So that's all you really need to remember for now. It gives you a more conservative estimate, which, if possible, we want to be conservative with our statistics. I will post up a link to the Khan Academy that discusses that in a bit more detail if you're interested in why that is in more detail. Okay, standard deviation. Well, as I already said before, the standard deviation is essentially an extension of the variance. And the reason we do this is because the variance is essentially, our variance is hard to interpret in some instances. And the reason why that is because the units that we see it in, it's in, again, squared units. So all the standard deviation does is really take it back and takes your variance and turns it back into a unit that's the same as the mean. Oh, you can ignore this here. I haven't got to that example yet. But all you do to get the standard deviation is you take the square root of your variance. So it's super simple to calculate once you got your variance. So let's just go through this again. Same example we had before. Calculate the mean. Subtract x minus the mean for each variable, for each value in your variable. Square that. Get the sum of that. Divide that by n minus 1, which again, 34.4 divided by 9 equals 3.82. And now to get the standard deviation, we just take the square root of 3.82, which is, I recommend using a calculator to do that. But 3.82, get the square root, gives us 1.95. Okay, picking back up where I left off, we'll go through one more example here to how to calculate this. Again, if we wanted to make this where it's the formula for the standard deviation rather than the variance, we simply just make it the square root of these. What I want to do real quick is take you guys through an example using the second way of doing it, but first I want you guys to calculate this using the way I just showed you. Take the following data set, which is the average amount of times someone has watched The Simpsons in the last month. Let's say we have 5, 7, 8, 11, 13, 18, 12, and 17. I want you to take a moment using the methods we just talked about and calculate the variance and standard deviations for that. So pause the video, do that, and then what I'm going to do is demonstrate the answer here using our second formula that we saw. Okay, hopefully you took the time to do that. But okay, here's our second formula. And the reason you might use this one is that if you have a pretty big data set, it's actually a bit quicker sometimes. And what you need to do here, what this essentially stands for, this sum of x squared, really we need two big things here. We need to get the sum of x squared and the sum of all of our x's and square that value. So this one basically means that, so this one here would basically mean that we take the sum of our values, so sum of x, which I've already calculated here, which would be 91, sum of x, and then square that value. So 91 times 91 gives us 8,281. And then we're going to divide that by n. Our n is 1, 2, 3, 4, 5, 6, 7, 8. So 8,281 divided by 8 gives us 1035.125. So we have this portion of our equation. Now let's get this side. This side, what we're going to do is just take x squared for each value and then the sum of that. So 5 times 5, 25, 7 times 7, 49, and so on and so forth. And then take the sum of all that, we get 1185. So the next thing we're going to want to do is essentially take that value, 1185, minus the first part that we calculated there, which was 1035.125. You can see I do this calculation down here. We get 149.825. So 149 point, let's just round that to 0.7, over our n minus 1, which would be 7 in this case. So then we calculate that, we get 4.63. Now that should approximately, depending on rounding differences, that should basically be the same thing you guys got calculating this formula the other way that we went over the first time. Now as far as the test and what you guys do in this class, you can use either formula to calculate the variance, and either one is going to give you the same answer. Now once again, if we wanted to get the standard deviation, we would just take this value, square it, and then bam, we got the standard deviation for that as well. Okay, a little bit more on the standard deviation, because that's going to be a very important concept. The variance and standard deviation are both very important. So basic thing, it tells us how closely the scores cluster around the mean in standardized units. Now that's got to be important here a little bit later in this class. But one thing that's really interesting about standard deviations is that if we have a symmetrical distribution, remember back to that portion when we talked about different shapes of your distribution, if we had a symmetrical one, then you would actually have it kind of come out like this, that 66% of your values would fall within the first standard deviation away from your mean. And then 2 standard deviations away, up to 95% of your values would fall within those 2 standard deviations. And then 99.7 would fall in 3. You can kind of see this visually here. 66, some of your values would fall within this 1 standard deviation away from your mean. And then you kind of go out a bit more, you get 95 here if you go out another standard deviation, and so on and so forth. Now this is a pretty important concept, but you don't need to remember much more than that right now. This is going to be really important when we get discussing this later with some other topics later in this class. Okay, just a few more things that we want to talk about with variance and standard deviation. The first is, once again, we talked about outliers when we talked about our measures of central tendency. Outliers can also affect, just like they affect the mean pretty strongly, they can affect your variance and standard deviation, which makes sense since your variance and standard deviation are somewhat based on the mean. They're telling you how closely the variables group around that mean. So what we would essentially get is that extreme scores would increase your variance and standard deviation, so they could essentially overinflate those as well. So that's another reason we have to watch out for outliers sometimes. Just a few other things to remember about variance and standard deviation. Again, they're both telling us to some extent or the other the spread of the variables around our mean. One thing that you want to know is that your variance and standard deviation can never be negative. So if you get a negative number of these, then you did something wrong. They can never be negative. Again, that's because we're squaring the values. So there's no way those could be negative. And they can actually only be 0 if all your values are the same, meaning there's no variation in your values. So these are actually pretty good measures of the variation in your data. Another thing that you get with variance and standard deviation is that the more spread out your scores are, so the more spread out they are away from the mean, the bigger your standard deviation and variance is going to be. While a small variance or standard deviation is going to tell you that most of your variables are pretty close to the mean. Or most, sorry, I said variables. Yeah, most of your values within your variable are pretty close to the mean. Now that can be pretty important because actually just by looking at your standard deviation, variance, standard deviation or variance in your mean, you can kind of learn something about the shape of your data right there. Because the standard deviation and variance, its size is in relation to the mean. So if you have a large standard deviation in relation to the mean, again, that can tell you that they're pretty far grouping away from it. But that's some of the stuff you want to remember for now. You want to know how to calculate these, and again, you guys have a test for this week. So for this test, you want to review all the stuff we've covered over the last couple weeks. Be able to calculate all the measures of central tendency, as well as all these measures of variance that we just talked about in this unit. Okay, but also you want to again read through your book. The book goes over a few things that I didn't cover here. Particularly, it talks about how to conduct these with the group data, which you don't need to know that as much, but you should read over that. Okay, as usual, if you guys end up having any questions while doing the homework or just reviewing the notes and that type of stuff, feel free to contact me. Other than that, you guys have a fantastic week.